Unit 3, Video Lecture 1, Historical Development of the Atom. Why does matter behave the way that it does? Can we predict how it will behave? What do we have to know in order to predict its behavior? The answer to these three questions lies in this. How is matter structured? Since the early Greeks, man has been pondering that question. The search for or the understanding of the structure of the atom has lasted over 2,000 years. Many people contributed to our understanding of the structure of the atom, coming from various countries and from many areas of expertise, including physics and chemistry. From this struggle came a new theory of the atom, along with a whole new type of physics. 2,000 years ago, the early Greeks began pondering this question: how is matter structured? The first to come up with something that survived today was Democritus. He was a Greek philosopher in 1460 to 370 BC. Now, the Greeks didn't have any technology available to them. Instead of that, what they did was they did thought experiments. And so he began pondering the question of division. If you're looking at matter, and you take a chunk of gold, for example, and divided it into two, do you still have matter? Of course, the answer is yes. If you take that smaller chunk and divide it in two, what do you end up with? Well, two smaller chunks of matter. If you kept on dividing and dividing and dividing, could you keep up with this forever? In other words, can matter be divided indefinitely? Democritus came to the conclusion that no, that matter is made up of a single particle called an atom that is indivisible. So the answer to our thought question is eventually we will get to a point where we cannot divide matter any further. He also decided that all atoms of the same substance are the same, and the arrangement of them determines what kind of substance is formed. During this period of time, there was also another predominant scientist named Aristotle. He disagreed with Democritus, saying that matter was made of four elements: fire, water, air, and earth. If you looked at each of the substances around you, they consisted of either one or all four of the elements combined in different ways. Clouds, for example, are made of water and air. Wood is made of all four elements. Aristotle was the premier scientist of the day, and therefore his theory was the one that was most accepted. And this kept on for another almost 2,000 years. In the late 1700s began the early days of what we refer today as modern chemistry. It was during this period that empirical evidence and conclusions drawn from not thought experiments but actual data collected during experiments was the predominant way of creating and supporting theories. John Dalton began experimenting with gases. So you know at this point that there was a lot of technology in place. First off, we had the capabilities of purifying various types of gases. We had ways of storing them. We had ways of mixing them together in a controlled fashion. So in his experiments with gases, Dalton concluded that substances are not made of fire, water, air, and earth. He instead began to understand that Democritus's view of the atom was more correct. Atoms are small. They cannot be created, divided, or destroyed. They're indivisible and indestructible. Furthermore, he concluded that atoms of the same element are the same. Atoms of different elements, therefore, are different. Atoms join together to form other substances, new substances. And when they do join together, they do so in whole number ratios, or fixed ratios. What you see on the right are the actual models that Dalton created. Time went on and we began to have the advent of more new technology, particularly in the area of electricity. Our understanding of electricity, starting with Benjamin Franklin and going on from there, increased over time, where we now have the capabilities of creating batteries, which was able to store electricity. We understood what electricity was all about. Not completely, but a much broader understanding. The word we use today, or electron, was created from our study of electricity. We also had vacuums that could create various types of tubes. one called the cathode ray tube. J.J. Thomson began experimenting with his own cathode ray tube. A cathode ray tube consists of two metal discs and on each end of a glass tube. Inside the tube there was a vacuum filled with only a small amount of fluorescent gas. We knew from other experiments that this gas fluoresced or began to glow when electrical current was running through it. What Thomson did was to create his cathode ray tube and then subject the ray tube to a magnet with a positive on one side, a negative on the other. What he found was that the negative plate actually repelled the stream of electrons coming through. The positive plate, on the other hand, attracted them. Coming to this conclusion, we know that the negative is a negative, positive is a positive, opposites attract, the same repel. Therefore, what Thomson concluded was that it is possible to divide the atom further, at least into two different parts, a positively charged part and a negatively charged part. Because most matter has no charge on it, the number of positives have to equal the number of negatives. It's called the plum pudding model. And in Thomson's plum pudding model, what he theorized was that the atom was basically a sea of positively charged particles studded with negatively charged particles, and that the positively charged particles contained most of the mass of the atom, whereas the negatively charged particles had very little, if any, mass at all. He called it a plum pudding model after a dessert that was popular at the time in England. 50 years go by, new technology. We now also have an understanding not only of electricity, but of radioactive particles, in particular the alpha particle. This began an experiment conducted by Ernest Rutherford. He created what's called the gold foil experiment, and this is a very famous experiment. It basically consists of a box containing radioactive material that was a source of alpha particles. Even though they weren't quite sure exactly what an alpha particle was, they had some understanding, and they knew what it was capable of doing. What he then did was he cut a small hole in his box, and he allowed the stream of alpha particles to exit the box, and then he further made them pass through a slit. This was to focus the beam of alpha particles as much as possible. That beam was then shot at an electrical foil. This electrical foil was pounded as thin as possible so that it only consisted of a couple of atoms in width. Wasn't quite sure what he was going to expect, but if Thomson's model was correct, that the atom was a sea of positively charged particles with studded with negatively charged particles, then as the alpha particles come in, they should bounce off each atom. He did see some of the particles bounce off each atom. However, the majority of the particles did go through. Rutherford's findings were that most of the particles passed right through. A few particles were deflected, a very few particles were greatly deflected. Based on this, he came to the following conclusions. The atom was mostly empty space. The nucleus, which was positively charged, was extremely small. And because it took up most of the mass of the atom, it had to be extremely dense. The nucleus was positively charged. Outside of the nucleus, therefore, to balance out and to maintain the neutrality of matter, were the negatively charged particles, in this case electrons, outside of the nucleus. Here's a picture of the plum pudding model and of Rutherford's atom. So, as we can see, with the plum pudding model, you have positively charged consistently throughout the entire particle, with negatively charged particles interspersed throughout. In Rutherford's atom, all of the positively charged particles were stuck in the center of the atom, with the electrons on the outside. James Chadwick was another scientist, and in this case he was primarily looking at the alpha particle. What he found was the alpha particle contained a positively charged particle. It also contained another particle that had no charge at all. He called that a neutron. We've come to know that inside of an atom you have not only positively charged particles, but you have neutral particles as well. Both the protons and the neutrons are in the nucleus of the atom, whereas the electrons are on the outside. Henry Moseley was a very talented and very young scientist. And in 1913, he used an X-ray tube to determine that the atomic number of an atom, which you see on the periodic table, and we're going to learn about a little bit more, is actually equal to the number of protons in an atom. Remember that Democritus said that atoms of the same substance are the same. What Moseley found was that atoms of the same substance all contain exactly the same number of protons. Unfortunately, Moseley was killed in World War II. In World War II, with the advent of the atomic bomb, we have a number of new types of technology now available to us. This led us to the development of what's considered the modern atomic theory. That begins with Niels Bohr, going from 1885 to 1962. What he showed is that the atom's electrons are capable of absorbing and emitting energy, but only in specific amounts. If you take any element and you subject it to energy, and then you take that energy away, what will happen is that substance will fluoresce. It'll glow. But it won't glow with all wavelengths. It'll only glow with certain wavelengths. If you remember from physics, each wavelength has a designated energy level. What Bohr suggested is that the electrons are not just willy-nilly around the outside of the nucleus. He said instead is that they exist in discrete energy levels. And he named those energy levels, he gave them a quantum number, 1, 2, 3, all the way up to 7. Here's another example of Bohr's model. Anytime you excite an electron and you allow it to move from one energy level to the next, what will happen is when that energy source goes away, the electron will fall back naturally down to its normal energy level. And as it does so, it will give off the exact amount of energy it absorbed in order to make that jump. So now we have a new model of the atom. Here's Rutherford's, where the electrons are willy-nilly around the nucleus, to Bohr's model, where there's a discrete nucleus and discrete energy levels, and in this case in layers outside of the nucleus. Electrons cannot exist in between the energy levels. They can only exist in those exact energy levels. The minute that Bohr published his findings, he knew that his model was wrong. However, it was a first step. The reason why he knew it was wrong is that any time you went to a larger atom than the one that he was working with, hydrogen and helium, his model didn't actually stand up. This leads us to the modern atomic theory, which we're going to talk a little bit more about in the next video lecture. What we found is that, again, the electrons do exist in discrete energy levels. However, those energy levels are not like orbits, or they don't orbit the nucleus. What they are is considered to be electron clouds, which are specific places around the nucleus. So, in conclusion, the current model of the atom is that an atom can be divided into three basic parts: proton, neutrons, and electrons. The protons and neutrons are in the nucleus, and the electrons are in fixed energy levels outside the nucleus. We do know also, and this will be handled in the next video lecture, is that protons and neutrons can be further divided. However, that's beyond the scope of our course. The number of protons in each element is unique to that element. It actually determines what the element is. The number of neutrons and electrons can vary from atom to atom of the same substance. However, protons are always exactly the same number. When elements come together to form compounds, they do so in fixed ratios. Thank you for watching this video.